Okay, I'm going to go through the first part of Chapter 3, Properties of Pure Substances. So this is what's going to be covered in this chapter, at least the main points. We're going to look at the concept, this idea of a pure substance, just basically intro to that. We're going to look at the physics of phase changes. We're going to look at the PV, TV, and PT, pressure, volume, and temperature diagrams. Pressure, volume, and pressure, temperature diagrams. We're going to look at procedures for determining properties of the pure substances, describe what is considered to be a hypothetical ideal gas. We're going to apply the ideal gas equation, look at this idea of compressibility factor for substances, and look at some of the best known equations of state. Okay, first part, pure substance. This one is if it has a fixed chemical composition throughout. Okay, so even though air has like several gases in it, it can be considered pure substance because it's homogeneous. It's basically the same proportion of the components through any given sample of it. Okay, so that's kind of what we're looking at. So just looking over here to the right to see that. So with air, so if you have different phases, in the same container, this case you cannot consider this to be a pure substance. Okay, so as long as it's there's no change in phase. So if you had liquid and air, water could be considered a pure substance when you have vapor and liquid together. Okay, but not air. And of course, the reason for water, it's made of the same element. Air is basically a mixture of different elements. So that's why this is the case for this, and why water could be in two different phases and still be considered pure substance. Okay, phases of a pure substance. And we can look at this diagrams to give us a different idea of, a visualization of these concepts. Basic idea, you could have an arrangement in three different phases. It could be a solid or liquid or a random, and in this case a random or gas phase. Okay, just visually showing what happens here. That when it's in a solid phase, everything's bound together. Of course, in a liquid phase, they can flow, molecules can move past each other, and then in gaseous phase, they're basically often can be often a random pattern, right? So phase change processes of pure substance. So the phase change processes of pure substances, and we have some terminology. First thing, let's think about water. Water can exist in three different phases, of course. And depending upon the atmospheric pressure and the temperature, you'll have it in different, potentially in different phases. Okay, so what do we know? And just in terms of changing phase, let's say from liquid to gas, what would happen if you had one atmosphere and got to 100 degrees C, which 212 in Fahrenheit, is that you're going to get a transition, right? You're going to get a transition from, you're right at the state where the water is transitioning from liquid form to vapor. Okay, so we think about a liquid that's right at that point where it's about to vaporize. We call that a saturated liquid. Okay, and the other, where not, if it's a compressed liquid, if it's not about to vaporize. And this example here is just saying, oh, okay, you have, you're applying heat, whatever, you're up to 20 degrees C. So this is not at a point where it would vaporize. at 1 atmosphere. But then when you get up to, if you keep applying heat, you got up to 100 degrees C, you're at a point where you would start to vaporize. Okay. Okay, so continuing on with more terminology. So we had previously we had this idea of a saturated liquid, and then from the other perspective, so if it's a vapor and it's getting to a point where it's about to condense, we consider that a saturated vapor. Okay. And then the other case is we have another one, of course, saturated liquid vapor mixture. This is when you have both. Okay, so you have both liquid and vapor existing in equilibrium. All right. Then a superheated vapor is one that's not a saturated vapor. It's not about to condense. Okay. So, here's an example of a piston and, some plate on here, piston and cylinder. And let's say that you're at 100 degrees C. So this is like a continuation from the previous slide. So you're adding more heat to this, and you're still at 1 atmospheric pressure, 1 atmosphere of pressure. And what's going to happen here is as you start to, you get up to 100 degrees C, 1 atmosphere, it starts to change over, right? So you start to get some vapor. So you have the liquid and vapor together. Okay. So this is considered to be the saturated liquid vapor mixture. Okay. The next state is here. Let's say that it's completely vaporized. So everything's vaporized. You keep adding heat to it, and you vaporized everything. You now have changed phase of all of the liquid into vapor. Okay. And now at that point, now you have it's all vapor at the third one. And you just keep adding more and more heat to it. And one of the things, just showing you visualization here is that what happens is, they start at 1 atmosphere, you start to expand. You notice the volume changes also as you're adding heat to it. So the vapor, of course, is taking up more space, okay, than the liquid. All right, so that's one of the things when we start talking about, it's going to be pressure, temperature, and volume. We're going to look at that. Okay, so we'll start by looking at a phase TV diagram, which is temperature volume diagram and what's actually happening. So if we're talking about like the states, and we can actually, go back and look at the previous diagrams to see it. What this is a process. We're going from so what do we have? We have compressed liquid. We heat up. So as the temperature increases of that liquid, we go along this path. And then as, you add more and more heat, what's happening here when you add more and more heat, like going from 2 to 3 to 4, this is where you're in this saturated mixture. So if you go back, the saturated liquid vapor mixture here, this one, 3. When you're in this state, you're adding more heat, but it's not, you're adding more heat, but it's not increasing the temperature. What it's doing is changing the water over from liquid state to vapor. Okay. And then when you finally get to 4, we'll go back and just look at that one. Okay, here's state 4. Now at that point, all of the liquid has been changed phase, and it's turned over into vapor form. Okay, and then as you add more and more heat, what ends up happening is that, and you look at the volume, right? It's like we add more heat, the temperature stayed the same, but the phase changed, and it's all that. Remember, this is all fixed at 1 atmosphere, and the phase has changed, so the volume has increased, but the temperature hasn't increased. Okay, then when everything's converted over to, or changed, all the water molecules have changed phase to vapor. Then as you add more and more heat, the temperature goes up, as well as the volume increases. Okay. All right, so the typical diagram for water. Okay, so continuing on with this idea. Okay, one of the things we got to pay attention to, right? So we have these 3 quantities, pressure, temperature, and volume. Okay, to look at. So, temperature which water starts to boil depends upon pressure, right? If pressure's fixed, so it's boiling temperature. So, what we could do is, we're talking about when we say that water boils at 100 degrees C, what we're really saying is 100 degrees C when it's at 1 atmosphere, okay? And the temperature which it changes phase at a given pressure, okay? So the T saturation temperature. And this one is the pressure at which the pure substance changes phase at a given temperature. Okay. So we can look at that. We can look at a graph, and for this one's water. Yeah, the numerical values are for water. So here's the saturation temperature. I'm sorry, saturation pressure and the saturation temperature. Okay. And like I said, this is the point at which it changes phase. So if we can, we could plot this out, but here it is over here in a table to kind of look at and see how this, relates to our experience. So this is what we get, when it's 1 atmosphere, 101.4, it's 100 degrees C. Okay, that word's saturation temperature when it starts to change phase, when water changes from liquid to vapor. Okay. And this is just plotted out. So what we can observe is, depending upon the temperature, we're going to get a different saturation pressure, right? So as the temperature increases, the pressure to give us that phase change would also increase. Okay. All right. So it gives you just a rough idea. What to get out of this right now is probably that it's the saturation temperature is going to be dependent upon, of course, the pressure and vice versa, right? So, and the saturation pressure is going to be dependent upon the temperature. Okay, and like I said, this is our typical experience for phase change of water at 100 degrees C and 101.4 kilopascals, which is essentially 1 atmosphere. So, continuing on with more definitions. Okay, we have latent heat. This is the amount of energy either absorbed or released during a phase change process. Okay, so if it's changing from liquid to gas, it's absorbing heat. If it's going in the other direction from vapor to or gas to liquid, then it's going to be giving off heat. Okay. One of the things that, like our table over here, you can think about like boiling temperature and how it changes depending upon your elevation. So 1,000 feet up, it's 96.5. So you can see even due to changes in pressure that you get different boiling points for water. Okay. All right. The next one is latent heat fusion. This is amount absorbed during melting. Okay. So for water or changing from solid to liquid. This is the amount of heat for that. Okay, so this is latent heat of fusion, latent heat of vaporization. Okay, so this is energy absorbed during vaporization, and of course it's the same as released. Okay, so this is going from liquid to vapor back and forth. Okay, and you're going to find that these are going to be dependent on the temperature and pressures involved. Okay, and here's just an example. 1 atmosphere latent heat of fusion of water is this many joules per kilogram, and this is what it is for vaporization. Okay, so these are like, if you think about the fusion and vaporization, these are our phase changes. Okay, depending upon which one it is, and this is saying okay for a fusion, it's this one, 33.7 kilojoules per kilogram, and then vaporization, which is a lot higher, is 2,256.5 kilojoules per kilogram. Okay, and like I said, I just talked about this table, but some more terminology as we go through. So one of the things, consequences of TSAT and PSAT dependence. One of the things this allows us to do is we can actually go and control the boiling temperature just by controlling temperature. Okay, so here's some examples. So continuing that idea, let's take a look at an example here. If you want to keep, like, let's say here's a test chamber and you want to maintain a temperature of minus 96 degrees C, and we're using liquid nitrogen to do that, one of the things we find is that to change phase, like from a liquid to a vapor, you're going to absorb energy in order for that to happen. Okay. Now, if you can limit that energy absorption by having like a heavily insulated, let's say this outer container or whatever is heavily insulated. So when you actually have this, like this vapor, this liquid nitrogen, when it's open to the atmosphere, what's going to happen is that, this minus 96 degrees C is the saturation temperature at 1 atmosphere. Okay, so what will happen then in this case is that, some of it's going to vaporize if you limit the amount. This is a small area, so whatever vaporizes basically just escapes into the atmosphere, or the room or wherever you are. This, because you're limiting the amount of heat and through thick insulation, you're keeping this bath at that temperature, and you're keeping it in that phase. Okay, if you didn't have this insulation here, of course it would, rapidly it would change over to vapor, because it would absorb heat from the environment and then change over to vapor. So if you wanted to keep a test chamber, in this case, if you're using liquid nitrogen, at that temperature, that's one way to do it. Okay. So the other part of this, of course, is that, you have to be able to have a way to either absorb heat or, dissipate heat into the environment. So this is one way where put thick insulation here, when it gets to that saturation temperature, because that's the saturation temperature for at 1 atmosphere. Okay, it's minus 196 C, because it can't, or you're limited to how much heat you can get from the environment. You can maintain that liquid state here inside this chamber. Okay. So in this example here, talking about vacuum cooling, and the basic idea is that you load some vegetables. In this case, like greeny vegetables typically are used for this, like lettuce or something, or spinach. So what you do is you keep the temperature the same, and then you lower the pressure. Okay. And what happens is when you get to at 25 degrees C and 3.17 kilopascals. So if we back up and we look at 25 degrees C, which is, basically ambient temperature, in a room, say, 3.17 kilopascals. Okay, that's the saturation pressure. All right. Okay. And that's, of course, where it starts to change phase. So then what happens is that, as it changes phase, so you get the liquid of the that's in the vegetables or whatever changes over to vapor, so it's allowed to be drawn out of the vegetables. So as you keep decreasing and decreasing the pressure, what's going to happen is eventually you get down to a point, like in this case, 0.61 kilopascals. And at that point, you've made the temperature down to essentially 0 degrees C. So you remove the heat from the vegetables. So you went through and cooled them. Okay. Okay, so we're going to continue on. Property diagrams for phase change processes. Okay. And we're going to look at the TV diagram. And this, I may have said volume before, but it's really specific volume. Okay, so this is specific volume also. Okay, it's a lowercase v specific volume. Okay, so if we look at this this graph with the multiple curves on it, what we're going to see is this one basically equates to, this is for water at 1 atmospheric pressure. At this point, this temperature, whatever, about this, like 100 C here, you reach the saturation point of the liquid. and then the saturated vapor point here is that, so you have it drawn out, and this is essentially the place where you're going through a phase change. Okay, in terms, and the volume is increasing, but the temperature is not increasing. Okay, or the specific volume is increasing, which essentially is the same for the volume per unit mass. Okay, so you're going along the curve. Temperature's not increasing. You're adding heat, and then eventually you get to this point, right? Okay. Now, if we take and we add weights, let's say we're doing it at an experiment inside a cylinder, and we have liquid in there, and we're adding heat to it, kind of what we previously shown in the previous diagrams, is that if you add weight to the top, you increase the pressure. And what happens? Well, a couple of things happening here, and you'll notice that in this case, the temperature at which saturation occurs is increases, okay, as well as the saturated vapor point decreases. Okay, temperature of saturation also decreases. It goes to the left. Okay, so this is when you get to the, this is saturated vapor and this is saturated liquid. So this transition line is decreasing in size. Okay. One other thing we'll talk about here is this idea of a critical point. And the critical point basically says, at this point you're getting to where the saturated vapor and the saturated liquid are identical here. Okay, so there's no more, there's no more of this flat line where you're getting that, adding more heat, you're getting this whole line where you're transitioning over to liquid. Okay. Or sorry, transitioning over to vapor from liquid. So just expanding upon that, going on to the next slide, we can talk about this idea of the critical point and supercritical pressures. Okay, we saw that critical point where we said there was no distinct phase change process in the previous diagram, and now what we're saying is that, like, this is the critical point, but afterwards, when we have pressures above that critical point, they're basically defined as supercritical pressures. Okay. Okay, so we'll look at the TV diagram and the PV diagram on the next slide, and we'll start to look at these different regions. So when we look at it from the perspective of defining regions, this is like this region here would be our saturated liquid vapor region. Okay, and then this is the compressed liquid region and the superheated vapor region. Okay, so this is dependent upon, of course, the pressures, right? So we have the saturated liquid line, we get to the critical point, and saturated vapor line. Okay, so this would be with varying pressures. Okay. Okay, so we can now look at the property diagram, the PV diagram, or pressure specific volume diagram. And in this case, the shape is similar to what we saw with the TV diagram. And this, if we look at this from a little bit different perspective, what we would say is this is like what we're trying to simulate here. Let's say we're taking weights off of the cylinder, so off the top of the piston, and we're lowering the pressure. Okay, so either, in this case, you can reduce the pressure by taking the weights off, and then we have the new graph, right, for that. So either going up or down, going up this way. And what we're going to notice here is that, of course, these lines represent for various temperatures. Let's say T1 is constant here, and this is just, for example, saying we're having T2 is also constant, but it's greater than T1 would be the next line up. Okay, but this gives you the shape, right? Same thing, same general shape, except we note that the pressure is decreasing to come down here, as opposed to before we saw the temperature was increasing, right? So here's the graph, the PV diagram. Here's our saturated liquid region, compressed liquid region, and our superheated vapor region. Okay, so at this point, if you get a rough idea of what this is representing, Um, that's really all kind of what you need to know for now. All right, then later we'll start to apply those. Okay. So one more thing, we can extend out these diagrams, and like I said before, you kind of get a rough idea of this for now. But we also have this idea of a triple point, and we can actually get to a point where, depending upon the specific pressure, temperature, um, and volume, depending upon what the volume is. But for water, if you have here's your specific temperature, um, um, triple point, and sorry, not specific temperature, the temperature of the triple point and the pressure of the triple point. At this point, if you have these, then you can actually get the three states together: vapor, liquid, and solid. And that's pretty much what this is representing. So this one, PV diagram, substance contracts on freezing, and this one is for ones that would expand, like such as water. So it looks a little bit different in how it works. You got this other little area over here. Okay, so basic idea, you have, we now have this solid, liquid, and liquid. If we just go back, and this is the PV, we'll go back and take a look and compare it. So we had like compressed liquid region over here. We didn't go far enough to actually include the solid phase too. Okay, so depending upon, in this case for the various temperatures, this is the graph you would get from that. Okay, and this is considered to be like the triple line, right? So basically, stating that it's the point or the multiple points, depending on the specific volume that you get where you're having the liquid, vapor, and solid all together here. Okay, all three, and that's, at least for the definition of triple point, what that is. All three phases together. Okay, so we also have another term, sublimation. This is when you're passing from solid phase directly into vapor phase. Okay, and you can kind of tell. You see where the solid is over here, and then the vapor is over here, and this is the line that's separating them. And this is the pressure, temperature graph. Okay, and then here's the different lines depending upon, it's after the triple point, what kind of substances that contract on freezing. And then this would be a different line if this is the vaporization line. Substances that expand on freezing. Okay. So one other point here is if it's below the triple point, you have this sublimation. Okay. So you're going directly into the vapor phase without going into the liquid phase. Okay. And we also have surfaces. Okay. So this is a little bit more involved. It's just kind of taking a look at this right now, just to show what it is, but it shows you in a three-dimensional, right? Because when we looked at these previous graphs, we had varying temperatures in these, here and here, right? We varied in temperatures, which actually gave us this curve. We could take it and also include that. So we have it's really a three-dimensional plot, or three-dimensional, it's a surface essentially, right? Because we also have temperature, okay? All right, so it just gives you the different ones. So the previous two, right? So we have the surface of the substance that contracts on freezing, and then the PVD surface substance that expands on freezing. Okay, so just surfaces gives you a little more. It has more information. It has all the information instead of just plotting the two-dimensional surface. So you can actually see where that curve comes from with the varying temperatures, right? And that's pretty much it for this first part.